let us now turn to the proof of the cell problem, which took the following form. The cell problem above, which we discussed in the previous lecture, has a unique solution within an arbitrary constant. And we are going to use Lax-Milgram's lemma in order to prove this theorem. But note that in Lax-Milgram's lemma, we had that if condition 2, 3, and 4 are satisfied, then we have a unique solution. But a unique solution period, not within an arbitrary constant. So we have to modify our problem a little bit in order to get this new conclusion within an arbitrary constant. And the trick is following. It may seem a little bit difficult to understand why we are doing this, but we have to do this. Instead of using the whole Sobolev space W pair, we now use a subset of it. And this subset is the subset of W pair, the space of periodic Sobolev functions, with the property that the integral of each function in this space should be equal to 0. So this means that the average value of the function should vanish. That is, be equal to 0. So we will start to show that Lax-Milgram's, the premises for Lax-Milgram's lemma is satisfied for all phi in this new space capital V. So let's first start with the property 2, the continuity criteria. And this, since the bilinear form A is exactly as for the Dirichlet problem, the proof is identically with the Dirichlet problem, word by word. So we don't go into this here. Just go back to this lecture on the Dirichlet problem, and you can see how we did it. It's a little bit change concerning the property 3. We are going to prove this, that A of phi is larger than some positive constant C2 multiplied with the square of the norm of phi. Recall again that the Sobolev norm of phi is given by this expression. It's the square root of the integral of the square of grad plus the square of phi itself. Remember that for the Dirichlet problem we used the Friedrichs inequality to prove property 3. And I also mentioned that we are either using Friedrichs inequality for this property, or we use Poincaré inequality. But Friedrichs inequality is only for the case when we have zero boundary conditions, which we do not have here. So we have to use the Poincaré inequality. And the Poincaré inequality took the following form. In our case, for all functions in the space capital V, we had that the integral of phi is equal to 0. Recall this property. So therefore we obtain a little bit more easy, a little bit easier inequality, and in fact same inequality as we did for the Dirichlet problem. And we now proceed exactly as for the Dirichlet problem. We add the integral of the gradient, the square of the gradient of phi on both sides of this inequality and obtain this inequality. And now we see that this is just the square of the norm of phi. So now we do exactly as we did before. We divide on both sides with this constant C0 plus 1, and after that we multiplied with lambda minus on both sides, and we obtain this inequality. And this inequality is exactly the same as we had for the Dirichlet problem. And now we have proven that A of phi is larger or equal to some constant which we can call C2 multiplied with the square of the norm of phi. So here we have now proven the property 3. Let us now turn to property 4. We are going to prove that L of phi is less or equal to C3 multiplied with the norm of phi. And in order to do this, we just use the Schwarz inequality. The Schwarz inequality, you remember, if just go back to the Schwarz inequality, it was concerning the integral of lambda u vector times w vector, and it was always less than the square of the integral of lambda times the first times the absolute value of the first vector u, and multiplied with the square of the integral of lambda multiplied with the square of w vector, or the norm of w vector squared. So that's what we have done here. So when we obtain this inequality, we recall that lambda is always less than the maximum value of lambda, which is lambda plus. And here we have this integral is also less than the integral we get when we replace lambda by lambda plus. So why are we doing this? Well, it's just because lambda plus is a constant, and a constant, any constant in the integrand we can lift out of the integral, and we lift it out of the integral, and of course we get this identity. So here we have both these two constants lifted out, and by multiplying them with each other, we obtain that this is equal to lambda plus. So what we are left with here is some integrals which are much easier to work with. The integral of the unit vector is the unit vector has an absolute value 1. So this is just the integral of 1, which is just the area of y. And now we can, as we did for the Dirichlet problem, we just add the integral of the square of phi, just in order to obtain the norm here, an estimate of the norm. Because now you see, of course, this inequality holds, because this integral here is strictly larger than what it would be if we didn't add this integral, because this is a positive value. And so this guy is just now the integral of this just the norm of phi, the square of the norm in here, and we take the square root of this and obtain lambda. So sorry, here it should not be squared, but it's only it's only the norm of phi here. And when we have obtained this, we have proven the step 4 also, that the linear form is also continuous. So what we have done here now is that recall that the bilinear form is given by this integral expression, and the linear form is given by this expression. And what we have here is that we have this weak formulation, that we know that these have a unique solution because the property 2, 3, and 4, all these properties are satisfied. So by Lax-Milgram's lemma, we know that U pair is a solution of this problem.